Good morning, good afternoon. I hope you're all doing well, and welcome to this webinar titled Optimizing Power Inverter Cooling with Generative Design. My name is Niels, and I will be your host today. I hope everyone can hear me correctly. If not, please let me know in the chat, then I can change my settings. Okay, let's jump into it. So today is all about power inverters, of course. The main challenges with power inverters is that the component is relatively small. So we have quite a bunch of chips on the bottom or on the top, or both top and the bottom, and they're all placed very, very close to each other. So the power density itself is quite high. Typically, these applications are liquid cooled. In the demonstration session or the demo session of this webinar, I will cover them. This application, of course, where we have an inlet and an outlet, and again, it is liquid cooled. Okay, but let's start with the beginning. The challenges of thermal design. So in the graph that I'm showing to you now on the x-axis, you basically see all, or a simplification at least, it's all potential designs that you can imagine: pins, fins, TPMS, all organic structures, even the empty one. They are all represented by this X arrow. On the y-axis, we then have the performance measure, and then the black line represents basically for each design what the accompanying performance is. We're talking about optimization, so it's counterintuitive, but the performance value, the lower the value, the better. The downside of this graph is we don't know a priori what this black line looks like. What we do know is, of course, our requirements. If our requirements are relatively relaxed, represented here by the green, the first green dotted line, target 1, we can easily see that quite a bit of the black line, the black curve, is below the thermal requirement, meaning that any design on this black line meets the thermal requirements. Even some local optima, like you can see here and here. In reality, most cases are not, or the thermal requirements, sorry, are relatively strict, represented by target 2 then, meaning that only a handful of, or a small data set of designs can potentially meet the strict thermal requirements. And then we have to go for we have to find the global optimum. Again, the downside, because we don't know what this black line looks like, we don't know where the global optimum lies. And this is where generative design can help you. So by generative design, it basically gives you a bunch of different tools to efficiently, or in the most efficient way, get to a design that meets the thermal requirements, be it the more relaxed ones or the quite strict ones. I can see someone put something in the chat. Okay, thanks for confirming that the audio is good. And then I will continue. Okay, and that's where we at Diabetics, where we pitch in. So we believe that smart algorithms can empower engineers by coming up with high-performing designs beyond human imagination and in automated fashion. Basically, that you as a thermal engineer don't have to spend too much of your manual time. Both ANSYS and Hexagon have acknowledged the strength of our software, have reached out to us, and we made them our technology partners. Okay, let's move on to actually designing power inverter. The design cycle I'm showing on the left is something that I'm sure most of you are familiar with, where you start with your geometry, of course. That's in the first step, empty. You create then a given cooling solution, for example, certain pins or fin arrangements that you know from previous experience, or that you saw online. You do then a CFD simulation or do some physical experiments. You post-process results, you analyze it, and then you loop through this until you find a solution. As you can imagine, I hope you can feel that it's quite labor intensive, and it's not the most efficient way, I would say, to get into that global optimum. With generative design, on the other hand, as I mentioned, generative design gives you tools to enhance your capabilities. And the first of those tools, or generative design, starts, of course, with the same empty geometry. And the first of those tools is to generate a bunch of different concepts. The concepts phase is a very important step of the design cycle, that you basically try a bunch of different things. For example, can aluminum be used, or can copper be used? Copper, of course, has a much higher conductivity, and thus will inevitably result in a better thermal performance. But copper is much more expensive and weighs more compared to aluminum. In the concept phase, you can try and figure out, is copper worthwhile? Is the potential, or is the improvements, relatively speaking, of course, is the improvement worthwhile over than cheaper materials like aluminum? Same with manufacturing techniques. 3D printing, highest flexibility, but for mass manufacturing at least, it's very expensive to make. While die casting is very cheap for mass manufacturing, but it's limited. The amount of shapes that you can generate with die casting are much more limited compared to 3D printing. So that's all stuff that you have to figure out, or that needs to be figured out as soon as possible in the concept generation phase. Once that's figured out, we then go to the detailed design phase, or the custom design phase, where you then improve a given concept further. So you lock in your manufacturing settings, your material properties, lock them in for then a detailed custom design to find then the most optimal solution. And if I go back to my graph from early in the webinar, it basically results in the following. By using the concept generation, you basically parse the entire design space, or at least parts of it, giving you a bit of an idea what that black line looks like. For example, concept 1 pins is in this area. Concept 2 pins with copper compared to aluminum is in this area, etc., etc., etc. And it might be, if your thermal requirements are not that strict, it might be that the concepts already meet your requirements. And of course, the work stops there. Most likely, you'll have to beat the more strict thermal requirements. Then the concepts will already give you a good idea of what to start from. That you don't have to start from scratch anymore, from completely fluid or completely blank design. But that you can use, for example, one of these shapes to further improve the performance, because it's much closer to the global optimum. Okay, I think that's everything I wanted to explain about this slide. Let's move on. And this is also how we configured ColdStream. So with ColdStream, in the first phase, or the workflow that you follow typically starts quite wide. You can try different options, narrow it down to the detailed design phase, and then widen out again. So in the first part, the fast concept generation, you try a bunch of different things, all those variables, to see what works best, and to see what you need to use further down the road. You then move on to the custom design, the detailed custom design, to extract the maximum amount of performance. And once that design has been locked in, you can then do further thermal analysis. For example, you have designed something, for example, for the normal flow condition, but you want to know what the performance would be, a small fraction of the normal flow rate, or much higher than the normal flow rate, to see how sensitive the design is, or to see how sensitive the performance is based on those variables. Okay. And now, I'll highlight in a bit more detail each of those different steps. So the concept generation phase, typically you will resort to more conventional cooling solutions, pins, fins, TPMS structures as well. And basically the main goal of it, or the main benefit of using more conventional cooling solutions, is that you can use correlations. You don't have to go with full CFD. You can use correlations to quickly evaluate a bunch of different data points. Of course, they will never be accurate, but the relative importance will give you a big clue what works best. And correlations are also fast, so you can generate a whole bunch of data to see what works best, and basically generate as much concepts as possible. That could look something like this, where you, for example, for each iteration, see what the estimated performance value is, and for each iteration, you can then see or get an understanding of what tendency works best. Copper, aluminum, lots of pins, not a lot of pins. 3D printing, more conventional cooling, more conventional manufacturing techniques. That's something that you can try and figure out within the concept generation phase. Okay, this I already explained. And then, of course, the manufacturing settings. As I mentioned before, 3D printing, the one here, is it's quite costly for mass manufacturing. It gives the most design flexibility, while more conventional techniques like die casting or sheet metal forming are much cheaper, but they don't offer as much flexibility. And the positive thing with generative design software in general is that you can fine-tune the settings to make sure that whatever the generative design software attempts or creates will meet your manufacturing techniques. For example, with die casting, you can put a lower or upper limit on the structure size, on the width of the structures. Similarly, you can constrain the angle, the release angle, to easily get it out of the mold. Similarly, with sheet metal forming, you can put an upper limit on the channel width size to make sure that no plastic deformation happens because of the difference in the pressure outside to the liquid. So that's something that you can use to make sure that that no unwanted or no unrealistic designs are being returned. And this is a nice example of what concepts on one side looks like, what you can expect from concepts, what you can then expect from a detailed custom design. So with the concepts, you a priori fix the design philosophies. For example, here, fins were being used, while for the custom design, the pattern looks much more intricate. For example, here on the top, CNC milling was used, so it's a more conventional manufacturing technique. But even with that more conventional manufacturing technique, the shape or the pattern, the cooling channel that's being generated is very complicated. It snakes through the entire space. If you then go for 3D printing, where you also allow for flexibility over height, you get a true spaghetti of cooling channels within your design domain. Okay, that's more of the technical side or the theory side that I wanted to cover. Let's now apply it on an example case. So the example case is a double-sided power inverter, where on both the top as well as on the bottom we'll have chips that produce the heat, 90 chips in total. And those 90 chips in total produce a little over 4 kilowatts of energy. The chips are then placed onto copper heat spreaders to easily spread out the heat towards the coolant. That's what's being shown here in orange. And then the housing of the heatsink is made out of simple aluminum. So we'll have a cover and a housing that are easily merged together. And then in between, of course, we will run our coolant with an inlet on the left running all the way to the back that enters then the heatsink. And then the outlet is on the right here and enters, or leaves, sorry, on the opposite corner. And in our case, we'll use water glycol. It's most common, one of the most common coolants that's used in electronics application, with an inlet flow rate of 9.5 liters per minute. And for goals, we'll optimize the temperature. So first of all, we want to minimize the temperature, or equivalently speaking, we want to maximize the heat exchange efficiency. And secondly, we of course also want to maximize thermal uniformity. The coolant enters here in this corner. The coolant is still cold, so it's very easy for the coolant to cool down these chips. On the opposite corner here, the coolant has heated up, so it's much more difficult for these chips to be cooled down. And that's what we want to counter with the temperature variance minimization. I want the temperature on the chips to be as uniform as possible over all 90 combined. You might think that it's quite difficult to set up such a case, but in actuality, it really is not. You simply prepare the CAD geometry in your preferred CAD environment, be it NX, Inventor, whatever you prefer. You upload it to ColdStream, and as with any other CFD software, you then provide the relevant input. For example, you specify what solids are used, aluminum, copper. You specify the fluids, is it air-cooled, liquid-cooled? In our case, of course, liquid-cooled. Next, you set the boundary conditions, inlet condition, outlet condition, as well as the boundary conditions, so how much heat is being generated. And then lastly, this is something very specific. You have to set the targets. You have to let ColdStream know what to optimize for. And that's, of course, our temperature targets, so temperature minimization and temperature variance minimization. And to make sure that the pressure level doesn't rise to infinitely high, we'll also put a pressure loss constraint on the inlet. And that's pretty much it. Once you provide all of that information, you submit the case. The generative design software will take care, will run the optimization, or will run the design process. And it will, of course, output intermediate data points and final results as well, of course, which you can then download in the instep file format. And if we, for this application, if we then delve a bit deeper into the concept generation phase, for example, we tried, for this particular application, we attempted using regular pins as a more conventional cooling solution, where we split the design domain up into two. So we have a design domain on the top, basically to help cool down the chips on the top. We have a design domain on the bottom, again, to cool down the chips on the bottom. And then ColdStream is allowed to generate a bunch of different concepts. So you can change the pin width, pin height, the number of pins, how the pins are placed. Is it a structured grid or a staggered grid? That's entirely up to the generative design software to dictate, and it'll just simply output those data points and provide me with information. And in the overall design performance or the design evolution graph, I can keep track to see what the software is doing. So on the x-axis, it shows the iteration count. So basically, it's a time step of all the designs that ColdStream attempted. On the y-axis, you have then your performance measure. And remember, the lower the value, the better. And then each iteration will have one of three colors. If it's red, it means it's infeasible. For example, it broke, for example, the pressure constraint. It's exceeded the pressure constraint, sorry. If it's blue, it means it's feasible, but at this point, not the best one. And if it's green, it means at this point, it is the best design. And this, of course, gives you a very quick overview of what design works best. Iteration 1, for example, was feasible. At that point, it was the only feasible design that was available, hence it's green. Iteration 2 was again feasible. It was better than iteration 1 because its performance value is lower. So that's our new green point. 3 and 4 are again feasible, but are worse than iteration 2. So we don't keep track, ColdStream keeps it blue. And in this way, you can easily see that iteration 23, the design that you see here on the right, is the best design of all 87 iterations that ColdStream attempted. So it reached iteration 23. It still tried to improve, but it couldn't find it. You may wonder why there's a difference between the number of pins top to bottom. And that's of course because the flow comes in horizontally and then drops down into the design domain. And by having a split or a different density, top to bottom, you promote uniform flow distribution top to bottom. And that's of course because of our temperature variance minimization objective. Okay, so basically that's the concept generation phase. You try a bunch of different things, and then you select the best concept to continue with if your performance goals are not reached yet. And it might be that with the first concept, you can get something, I'll call it scenario 1. You can get something like this, an intricate spaghetti of different cooling channels. But it might be if you use a different initialization, a different concept to start with, that you get an entirely different design, something that looks like this. Again, something very something very intricate, with then of course slightly different performance measures. And then it's up to you to decide, is this sufficient? If not, it might be that it's simply not feasible to meet the thermal requirements, and then you have to basically go all the way back and rethink the entire geometry. Okay, that's everything that I wanted to highlight in the slide deck. I will first answer questions, and then I will show it for the ones who are interested. I will show it on what it basically looks like on ColdStream. But first things first, are there any questions? Feel free to put them in the chat box. The first question that comes in is to explain a bit more about the graph that I showed here. Yeah, okay, oh, sorry, that's too far. So the first question that comes in is to explain this graph a bit more in more detail. No worries. So on the x-axis, it's a very simple. It's a simplification because we can only think, or we can only easily see in 2D, at least on a slide. So this line basically represents all potential designs that you can think of, be it no structures, low density pins, high density pins, those spaghetti-like channels that you saw later on the slide. All of those are somewhere here on this line. And on the y-axis, we then have the accompanying performance measure. So basically, as if you run a CFD simulation or a correlation with one of those designs, you will get an accompanying performance value. And that's represented by this black line. The only downside is we don't know what this black line looks like. We can, if you have infinite time, you can draw all potential designs, and then in the end you can draw it. But it's that's not efficient. That's not the goal of what we want to do. For that, we'll use the some smart features of the generative design software. The first one being concept generation. So where you a priori select a given design philosophy, pins, fins, gyroids, and then quickly evaluate a bunch of different options. Because you use conventional cooling solutions, correlations can be used to quickly identify the performance based on the correlations, and to basically generate a bunch of different data points that you can somewhat get an idea of what this black line looks like. It might be that one of those concepts already meets your requirements if your requirements are not that strict. It might be that none of those, or most likely none of those, will meet it, and then you can still use these concepts to basically use them as a starting block to further improve the performance, to get to that global optimum that you then need to look for. That's basically what this graph looks like. I hope that answers your question. In the interest of time, I will now move to ColdStream to showcase it, showcase the demo that we just highlighted, how we tackled that problem. You should now be able to see ColdStream? Yes, you can. So on ColdStream, you'll most likely want to do the navigate to the projects tab, the tab where you do the bulk of the work. And then I will scroll down to this particular project folder. Inside our project folder, that's where you will do the actual work, where you will actually do the actual set up the actual cases. Where simulations are just regular CD simulations. If you have an existing design, you want to know the performance, you can do them a regular simulation. Standard design is our concept generation, so where you will use standard designs, pins, fins, etc., to generate a bunch of different concepts. And then custom design, of course, that's our topology optimization. That's our custom design where something custom will come out of the optimization. We of course start with some regular CD simulations to make sure that everything is set up correctly, that it makes sense. We'll then do the concept generation, try a bunch of different things, pins, materials, shapes, manufacturing settings, to then narrow down to one or two designs that are promising to further improve, to maximize the performance out of. Oh, no, that's okay. And then, as explained, if you then, for example, move to a finished case in the design evolution, you then see the how each design, how each iteration, how the performance is then evaluated, and how they compare to one another. So, for example, here in the first iteration, not a lot of generated, so hence performance is of course not that good. But iteration 23 is the same iteration that I showed in the slide deck. The number of pins has increased dramatically, and that's of course also reflected then in the performance measure. Okay, that's everything that I want to explain. Are there any further questions in the? If so, feel free to put them in the chat box. If not, then I will thank you all for attending this webinar. I hope you found it interesting. Thank you also for participating, and I wish you all a very pleasant day. And I hope to see you in the next one. Have a nice day. Bye bye.